No? Some, who yes? Raise your hand. Who no? Okay, so good. The nice thing about this point on is I assume that everybody's on the same page. So I assume you haven't seen it and we're all on the same page. In chapter P, I was moving through some things quickly because I assumed that you knew them. Some of you got kind of ground up in the gears there because you may not have remembered it, but now we're starting from scratch. As I mentioned, only 3 topics in calculus: limits, derivatives, integrals. Limits is chapter 1. When we're done with chapter 1, then we move on to derivatives. That'll be most, if not all, of the rest of first semester, and then we get into integrals in second semester along with derivatives. Okay, now obviously that's broken into smaller pieces, but we'll go from there. Okay, so here we go. Today you should be able to estimate a limit using a numerical approach and a graphical approach. I prefer the graphical approach, but it won't always work out that way. What happens when you can't find a limit? Why isn't there a limit? Are you sure there's no limit? This one's a little shaky. There are 2, maybe 3 lessons in the year that are just going to melt your noodle. This is one of them. And so I'm going to simplify it a little bit, and this doesn't come up till the back end, which is the formal definition of limit. It's not something in our curriculum, but I think it's something you should be exposed to. So I'm going to dumb it down as much as possible, and we're not going to spend as much time doing it as we would, let's say, if they're in a college course or in even in BC. And like that says there, try not to get your brain melted by the formal definition. That's at the back end of the slideshow. The front end is a little bit more realistic and easy to handle. Okay, so here we go. Introductions to limits. What is a limit? So let's suppose we have this function. Do you have any idea what that function looks like? No, and I wouldn't expect you to. Let's talk about the notation first. This is saying what is the limit of this function as x gets closer and closer to 4. A couple things could happen at 4. It could just have a value. It could have an asymptote. It could have a hole. It could be undefined there completely. There might not be a value. And that's going to change as we look at each and every function. Okay. A limit by definition is real simple. What's the y value as I get closer and closer to that x value? You with me? Yes or no? Yeah. It's not rocket science. Good. So first thing you're always going to do with limits is plug and chug. Okay? Plug and chug meaning take 4, put it into the function. You might want your calculators, by the way, because I'm not going to do all the work for you. But I did in this case. If you plug in 4, you get 0 over 0. And by now, you should recognize that's a bad thing. I mean, I don't even know what that is. What is that? Is it 0? You see why this could be 0, right? Maybe not. What would make that fraction equal to 0? The numerator is 0. Good. This fraction could be undefined. Why would it be undefined? Denominator is 0. This fraction could be equal to 1. Why? Same numerator, same denominator. What's the correct answer? There isn't one. It's undefined. It's 0. It's 1. It's a mess. We don't actually talk about this until second semester. We just avoid that like the plague. This is bad. Okay. You put 4 in for x. You simplify your ratio. You get 0 over 0. That's a big problem. But I will tell you that this plug and chug method is the first thing you're going to do for all limits from this point on. And it's something that people forget. Because we're going to talk about other techniques. What else can we do to find the limit? What can we do to simplify things, et cetera, et cetera. But people always forget the most simplest thing. Just plug in the value, see what happens. Okay. So now that doesn't work. I don't know. I don't know what the picture looks like. I can't just plug in 4 to get an answer. What else can I do? Good. How? Factor that bad boy. Okay, go ahead, factor. A little practice for you. Don't know if I did. I'm going to click anyways. Oh, I remember this. respect you if it was a new one. At 209? Is that what it's called? You have no clue, do you? That's a shame. Have you ever seen the movie? All right. Well, some people would wear stuff they've never seen. I got it. Michael, did you actually walk for diabetes there? Okay, good. That's respectable. Patrick's actually in the U. That's respectable. Okay. Did you wrestle at, sorry, it's track. Did you run the track, Cougar Track Classic? You threw an air thrower, yeah. Shot put, discus, both? Small children? You ever try that? You threw Dante? How hard to throw Dante? Wow. Do you have like bird bones? You weigh like 40 pounds? All right, what happens? Did you factor it? How's the top factor? And how's the bottom factor?
3x plus 5.
Not so good on the bottom, huh? Anybody else? Emily got it?
3x plus 5 and x minus 4.
Well, I don't know, let's see. Oh, where'd that come from? What am I missing? Raymond?
X minus 4s cancel out.
X minus 4s cancel out, beautiful. Ooh, that's nice. Okay, so let's finish the limit problem first, and then we'll come back and talk about the graph of what that's doing. So I simplified it algebraically. That's the second thing you should check. Number 1, plug and chug. That doesn't work. Number 2, algebraically manipulate the function. Factor top and bottom, see if things cancel, boom. Step 3, plug and chug again. So now what happens when I plug 4 into there? You can all do math, right? No? Give you a chance to get caught up. I'm sure you're all calculating like mad people. Sid, what happens when you put 4 into that function?
I got 15 over 17.
15 over 17. Can somebody confirm?
Yep.
We're good. Is that a valid answer, Sid, you think?
Yeah.
Works for me. Okay, 15 over 17. That's our limit. Now that's great, but what does that mean graphically? So let's back up. The original function was some graph. I have no idea what it looks like. It's a parabola over a parabola. When I graph it, I don't know what's going to happen. But then we factored it, and the x minus 4, was it x minus 4? Yeah, the x minus 4 is canceled. How does that show up on the graph? Maggie? There's a hole, correct. Okay. Where is that hole? X equals 4, y equals? Y equals? No. 15 over 17, correct. Okay, so the thing that people get bogged down on is they think, let me draw a picture here because we're visual, some of us, oh, there's some algebra or geometry for you. So let's suppose our graph looks something like this. And this would be at 4. And they say, well, there's no limit there. How can there's no limit because there's nothing there. But you have to remember what I said originally. Limit is the y value as you get closer and closer to that value, not necessarily the value at the function. So if we have a nice simple function in green, let's say, okay, and I want to take the limit here at -2, well, what's the limit at -2? It's just the y value, done. Well, what happens in the blue part? Well, I'm getting closer and closer to this 4, but can I ever really get to 4? No, because I have a hole there. How big is that hole? Sorry? So again, let me ask my question. How big is that? Or I should say, how small is it? Very small. How small is very small?
Just one top whole line.
So how big is it? In other words, how wide is that hole? I'm sorry?
However wide. Oh, that would be too easy.
It's infinitely small. So I can go to 4.0001. I can get to 4.00000001. I can get as close as I want, I just can't get to 4. So even though we're putting a hole in there and it looks like a big circle, you have to think about that hole as being infinitely small. Because we can get closer and closer to the function, or to the value, I should say. Okay, so here's our notation. Again, refreshing the notation here. We're taking the limit of a function as we get closer to this value of a. Well, what is a? It's whatever number we want it to be. In this case, it was 4. And when we do that, we get a value for the limit, which we call capital L. Remember that this is a y value, not an x value. This is my x value down here, the a. L is the y value. Are we good so far? Anybody completely confused, or are we kind of on the, we're rolling along okay? Good. All right. So there's our picture. Again, if you're, that's not necessarily the picture of that graph, it's just some function. And so I want to know, here's my f of x curve. I want to know what's the limit as x gets very close to a, and I can come from the right, go this way, or come from the left. As I get closer and closer to that point, I'm going to get closer and closer to the L value, which is the y value. Doesn't have to be defined at the point. You just have to be able to get really close to it. So that's the concept of limit. Before we move on, where things are going to get more confusing, are you okay with this? If not, I'll explain a little bit more. Go ahead.
So is there going to be a hole every time?
Not necessarily. Because this function, for instance, has no hole, so if I ask you what's the limit at a, it's just going to be the y value of the function. That's why we plug and chug first. Because if there's no holes, asymptotes, or weirdness going on, then the limit is just the value of the function at the point. Okay, question?
So if there wasn't a hole on the very first example and you plugged in 4, it would have gotten something that wasn't 0, 0.
Correct.
Okay.
So if I take the limit, let's say as x approaches 2 of x squared, I would just get 4. Because that's what we're getting closer and closer to as we get closer and closer to 2. Okay, go ahead.
So you know there's a hole if they choose 0 over 0.
No, you know there's a hole if 2 terms cancel. So when you factored, we had the x minus 4s that cancel. That x minus 4 is what generates the hole. What about that guy? Okay, so again, refreshing the notation there. We're wondering what's the limit of 1 over x as x gets closer and closer to 0. So the first thing you might want to do is draw a sketch of 1 over x. That's one of our mother functions, so you should know it. Patrick, what's that look like? Uh-huh. And? What's the other half? Anybody else? Sure. You just want to use the smart board, don't you? Sure. Beautiful. Oh, that warrants a golf clap. Let's give it up. So let's pretend, let's ignore that problem for a second and let's look at this problem. What is the limit as x approaches 2 of 1 over x? Yeah, don't overthink it. It's just 1/2. Because what's the first thing you should always do? Plug and chug. So this is 1/2, easy. That's over here. We're at 2. It gets closer and closer to 0. No problem. What about the limit as x approaches -10? -1 over 10. Good. So we're okay with all of that, right? What about 0? Wait a minute.
It's not possible,
Why?
because there's a 0 denominator and it's undefined.
Good. Okay. It's not possible to plug and chug because we get 1 over 0, like you said, it's undefined. So we have to come up with a different way to do this. So let's suppose I start from the right-hand side, and we'll talk about this a lot. Right-hand limit comes from the right versus a left-hand limit, which comes from the left. What if I start at the right and I start traveling along this curve? As I get closer and closer to 0, what's the y value getting closer and closer to? Infinity, correct. We're all good with that, right? This keeps going up. Does it ever hit 0? No. Okay, and remember that infinity is a concept, not a number, but that's irrelevant. What if I start here on the left? Negative infinity, correct. That causes a problem. The right-hand limit in this case doesn't match the left-hand limit, and we can't have that. Okay, so let's go over here. There's our graph, not bad. So here's our first theorem about this. What is that notation saying? So write it down first, because it's important, and then I'll explain the notation. This is one of the more important theorems that we'll deal with in this chapter. And a lot of times what we'll do is I'll give you the fancy calculus speak, and then I'll give it to you in English so that you can understand what it's saying.
Mr. Reed, in the second limit statement, does
Yeah.
the A have something over it?
Yeah, that's not over it, it's behind it, it's a minus sign.
Oh.
And then this has a little plus sign. Okay, and I'll explain that in a second. Okay, so what this is saying, in order for there to be a limit of f of x when x approaches a, in other words, in order to get a value of L, these two things have to be true. You'll remember, well, maybe you don't. This double-headed arrow means if and only if. Okay. This is going to be true. There will be a limit only if the limit from the left-hand side, that's what the minus sign means, from the left-hand side matches the limit from the right-hand side. So now we start looking at three different limits. There's the limit at the point, there's a limit from the left-hand side, and there's a limit from the right-hand side. So we did the right-hand and the left-hand side. The limit from the right-hand side, you said, was positive infinity. The limit from the left-hand side is negative infinity. Does the right hand match the left hand? No. That means no limit. And we represent that by saying DNE, does not exist. Not empty set, does not exist. Okay? This is a real important concept, so I want to make sure you got it here. In the previous problem, when we approached 4 from the right, we got that value of 15/17. When we approached 4 from the left, we also got the same value of 15/17, because there was just a hole there. Therefore, the right-hand limit matches the left-hand limit. We're good to go. The limit is 15/17. This is different. You'll see this a lot around asymptotes. One side goes up to infinity, the other side goes down to a negative infinity. Right-hand limit doesn't match the left-hand limit.
So is it DNE for anything that's from 1 over?
Not always. Because sometimes they'll go like this.
Okay.
Yeah. It would be nice if it was that easy, but that's not always going to be the case. Okay, so you understand the theorem here. Okay.
What happens if they do go to?
We'll talk about that when we get there. Okay, because there's a couple possibilities there. What would you think would happen?
They would need it.
Because the right-hand limit is infinity, the left-hand limit is infinity, and therefore the right-hand limit matches the left-hand limit, so therefore the limit is infinity. Sounds good to me, right? Yeah, but we'll see some problems there that we'll get to later. Okay, so there it is. Right-hand limit. So abbreviation is LHL equals RHL. Left-hand limit matches right-hand limit. So you will get some problems where it will say, what is the limit as x approaches 0 of 1 over x? Justify your answer. One way you could justify is to spout this theorem, which really, who's going to remember this theorem? Realistically, you're going to say there is no limit because the left-hand limit does not match the right-hand limit. Okay, we're good? Excellent. Okay, what about this guy? So this is similar to what we did before, where we have a parabola, that has a hole at 1, 3. What's the limit as x approaches 1 from the left? As I approach 1 from the left, what's my y value? 3. What's my limit as I approach from the right? 3. Is there a limit at 1? Why is it 3? Again, don't overthink this. From the left it's 3, from the right it's 3. Is there a limit at 1?
Yeah.
Yeah, it's 3 because the left-hand limit matches the right-hand limit. Okay, does that make sense? Again, this is very similar to the previous problem we did. Okay, good. Holes do not usually cause problems. You just have to find the hole, and sometimes that involves simplifying. Okay, so obviously you need to factor a cubic, and then it would cancel with the x minus 1. Yes, sir.
I'm confused. When would the left-hand limit not equal the right-hand limit?
Can you wait 2 minutes?
Oh, yeah.
Okay, I got some examples.
Okay, I thought it was, yeah.
Other than the asymptotes we looked at, I'll show you another example of
Okay.
one where it doesn't work. Let's suppose, just as a sidebar here, forget about this problem. Let's suppose we had a function where we had something like x minus 2 in the denominator, and that doesn't cancel. What happens at 2 then? What does that generate graphically? No. If it cancels, it generates a hole. If it doesn't cancel, what do we get graphically? So in other words, for those of you that are visual learners, what about 2 over x minus 2? You get an asymptote, correct. Wherever the denominator is undefined, you get an asymptote. And that's going to cause all kinds of fun, never mind. Okay, so we got a function there. X over the square root of x plus 1 minus 1. Any idea what that looks like? No? Good, because I'd be worried about you if you did. What happens when we take the limit at 0? What do you do first? Plug and chug, and what happens? 0 over 0. So now you need to algebraically manipulate. Here's the $64,000 question. What the heck are you going to do to that function to manipulate it? Well, before we take a look at the chart, what could you do to manipulate that function? Michael?
Square it.
Good. No, can you square it? No. Sorry, because we don't have an equation, we have a function. In order to square it, you got to know what both sides are equal to. Are you familiar with the term conjugate? What is a conjugate, Regan?
For this one, it would be x square root of x plus 1 plus 1.
Correct. Okay. We're not going to do the math because that's a little nasty when we just hit the ground running. But you would multiply by the square root of x plus 1 over the square root of x plus 1 plus 1. And then when you multiply it out, you'd see how things simplify. We don't care about that. We can take another approach, and that is a chart approach to finding that value. So if you plug this into your calculator, you can start plugging in numbers that get smaller and smaller. We get closer and closer to that value of 0, and you can see what y values we're getting closer and closer to. We're getting closer and closer to 2. You're not really going to do that because it's time-consuming and silly, but in some instances, it might be easier than doing the algebraic manipulation of that bad boy. So you have an option there. The other option would be to graph it on your calculator and see what that looks like. Okay, that's what the graph looks like. And you see that at 0, we're getting closer and closer to 2, so that tells us exactly what we thought was correct in the previous line. Okay, so now what happens when you have no limit? It fails to exist. In other words, you put in, you plug and chug, you don't get a value, and weird things start happening. How are you going to handle that? Okay, so Jimmy, this addresses your issue. We talked about that function already, right? That's one of our mother functions. If not, you should have it in your notes somewhere. and realize what that looks like. It looks like, I think I have a picture of it here. Yeah, there it is. Okay. So from 1 to the right, -1 to the left. So here's a function that doesn't have an asymptote, doesn't have a hole, but is still going to cause some problems as we get very close to 0. Okay, now, well, let me write this all out. What is the limit as x approaches 0 from the positive side of f of x? What is the limit as x approaches 0 from the negative of f of x? And what is, we'll do it over here, what is the limit as x approaches 0 of f of x? Okay, so let's break this down. Positive means we're coming from the right. Max, what's the limit as I come from the right of this picture here? What am I getting closer and closer to?
0.
Nope. Remember, it's the y value.
Oh, 1.
1. Good. Everybody in agreement? Good. Max, keep going. What about the left side?
Also, -1.
Good. Now, how about the overall limit with no direction?
0.
Nope. Anybody want to help them?
And they're not the one because the right hand limit has nothing.
Does not exist. Okay. That's an important point. Is everybody good with that? Why? Say it again.
Because the left hand limit does not equal the right hand.
Left hand limit does not match right hand limit. That's your justification. Okay. 2 different values up here, which means that can't have a limit. Sure, I'm getting closer to 1 coming from the right, but from the left I'm getting closer to -1, and that causes a problem. Just for giggles, to make sure we're all on the same page, what's the limit as x approaches 2 of this function?
Just 1.
1. Why, Dante?
It's 2 over 2.
Yeah, plug and chug. Okay. That's not a weird point. There's no strangeness happening at 2. 2's just sitting over here doing its own thing, which means it has a value of 1. Okay, it's when you get to this kind of stuff, this weirdness, that's going to cause the problem. Does that help?
Yeah.
Okay, good. Gesundheit. Okay, we good with this? Now I don't know if we're ready for the funness net yet, but yeah, we did that already. Okay, there we go. Excellent. So here are 3 scenarios that are going to cause problems. The first one is the most common. Right-hand limit doesn't match left-hand limit. Does not exist. Increases or decreases without bound as x approaches c. That's a fancy way of saying it goes to infinity or negative infinity. And then the other one is kind of weird. If it oscillates between certain numbers, like sine functions, for instance, cosine functions oscillate, that's going to cause some problems. They are in order of, what's the word I'm looking for? Commonness, that's a word. We will seldomly, if ever, see part 3, but it does pop up every once in a while. And of course, I'll have a couple theorems or a couple functions for you where it does, just so you've been exposed to it.
So that doesn't match the left. Is that what's the other graph?
Yeah, a lot of times that happens either like the one we just had or it's asymptotic. Okay. Are we good with this? Okay.
Can you explain the last one?
You might have a function that oscillates back and forth as it gets closer and closer to a function. There are things called resonant functions where it just keeps bouncing up and down as it gets closer and never really hits that point. So without getting too nerdy on you, you might have a function like this that starts out here and goes and as you zoom in on it, it's still the same thing. You zoom in, it's still the same thing. So it never approaches that value, but it wouldn't have a limit because it's not getting to that point and it's bouncing between a high value and a low value. Okay. Again, not very common. Okay. Let's take a breather for a second because this is going to be painful. If we did the formal definition of the limit, some of you would run out of here crying, running for the dog. So we're not going to do that. We're going to dumb it down. And there are a couple things you need to get out of here. The most important thing is that you can speak intelligently about three things: epsilon, delta, and the neighborhood. Okay? And so I'll try to get this under control so you understand what's going on. We've done the practical approach to limits, how to actually find limits, what makes a limit work, what doesn't make a limit work. This is the calculus that justifies this, and this is kind of nasty. So I'm going to skip through this. In fact, you know what? Just put your pens down, or pencils, your writing utensils down, and just be mathematical sponges and absorb information. Okay? So we're going to take a function like this. So here's my function. I have my starting value c, where I want to find the limit at. And by the way, we switch back and forth between c and a. I don't understand why they do that, but if we're talking about the x value, they call it a sometimes, they call it c sometimes. We called it c. And I'm going to move a little bit to the left and right of c. That distance that I move is called delta. That's a lowercase delta. I don't know if you can see that, but it looks something like that. Okay. When I move a little bit to the left and right of c, that's going to generate some values up here. So aside from moving to the left and right of c, I also move up and down from this limit value. That distance that I move up and down is called epsilon. It looks like a weird E. Okay. So there's delta and epsilon. Delta is the distance that you move along the x-axis. Epsilon is the y value that you move up and down from the limit. Okay. If I take this distance and I take it across, I get these two horizontal lines. And if I take the c plus delta and the c minus delta and extend these up, I get some vertical lines. This little guy here is called the neighborhood. Okay, so the neighborhood is the rectangle that's generated by the epsilon and the delta. Okay. Are you good with that? Okay. Not that difficult. So the question is, what's delta? How big is delta? How big is epsilon? Here's the weird thing. They can be as big as you want them to be, within reason. You don't want delta to be 3 billion. You want it to be something very small. And in actuality, when you start talking about the formal definition of limits, delta and epsilon get very, very, very tiny. So we want a small neighborhood. In order for the function to have a limit, then it has to have values everywhere in the neighborhood. So if you can see, I drew over it, but if you can see that function in there, that function has values everywhere in the neighborhood except for this point that we're dealing with. So the a or c value doesn't matter here. All that matters is the rest of the neighborhood. Okay? Does that make any sense? All it does is say, yeah, there's a limit because all the points in the neighborhood except for a or c have values on the graph. Now, that's nice and easy, but what happens when it doesn't work? In other words, what is it going to look like if it's not or doesn't have a definition? Okay, so let's go back to, where is that picture? Come on, this guy. Okay, so let's talk about the, and I already put the deltas in there. Let's talk about the neighborhood, or let's generate a neighborhood around that point 0. Okay, so here are my deltas. Go up like this, go up like that. There are my vertical lines. And now around that limit value, I need some L plus epsilon and L minus epsilon. How big do I want to make epsilon? I can make it as big as I want. So I'm going to come up here and down here. It has to be the same value, by the way, same up as down, and then I get this. Okay, so there's my neighborhood. And just so I don't write over it, I'm going to trace it in green. Any problems with generating that neighborhood? You see what I did? Okay. Pick some deltas. How big are deltas? Doesn't matter. Pick some epsilons. How big is it? Doesn't matter. Why does that not have a limit? Because notice there's some area over here that doesn't have any graph in it. And as soon as there's no graph in it, it doesn't have a limit. Okay. Does that make sense? Well, let's make the neighborhood smaller. So instead of doing all the drawing here, I'm just going to do that. Okay? That's not the best drawing in the world, but you get the idea. Now does it have a definition? No, because there's still area to the left of the value that has no part of the function in it. Okay. Does it matter how big I make the neighborhood? No, because eventually it's going to shrink. Now you could cheat. You could cheat and make a neighborhood like this. But again, that's not realistic. We're talking about very, very small values for delta and epsilon. Okay? Can you intelligently converse about delta epsilon in the neighborhood now? Yes or no?
Yes.
Okay, good. So then if we go back, we can look at all the math involved, but nobody's going to care about this. So and then L and then the epsilon, we got that, we got the neighborhood, good, everything's good. And then, oh yeah, you can put the epsilon into F, and then it gets C over there with deltas, who cares? And then you got all that. Yeah, okay, we're done. So, there's your approach to solving limits. Plug and chug first. Always plug and chug first. Because that might be as easy as finding the answers. If it doesn't plug and chug, then algebraically manipulate it. Factor the top, factor the bottom, simplify things. You can look at the graph. You can guess, you can pray, you can plug and chug again. 4 and 5 are up to you, depending on what you want to do, but I would definitely